Today we will discuss random forest, one of the most popular and powerful machine learning algorithms. Random forest is an ensemble learning method that combines multiple decision trees to improve prediction accuracy and reduce overfitting. Instead of relying on a single tree, the algorithm aggregates predictions from many trees, producing more reliable and robust results. Random forest is widely used in engineering, healthcare, finance, and many other fields because it can handle complex nonlinear behavior of the dataset. This slide introduces the core idea of random forest. Various engineering datasets such as asphalt, pavement, traffic, concrete, materials properties are used as input to the model. Instead of relying on a single decision tree, random forest builds multiple trees, each trained on different subsets of the data. Every tree generates its own prediction, and the predictions are then combined to majority voting for classification or averaging for regression. By combining many trees, random forest reduces overfitting, improves prediction accuracy, and produces more reliable results for engineering applications. Before discussing random forest, it is important to discuss the limitations of a single decision tree. While decision trees are easy to visualize and interpret, they are often sensitive to small changes in the training data. A slight change in the dataset can produce a completely different tree structure and prediction. Random forest was developed to overcome these limitations. By building many trees using different subsets of data and combining their predictions, the model becomes more robust and less sensitive to noise. As a result, random forest generally provides better prediction accuracy, improved generalization, and lower risk of overfitting compared with individual decision trees. The idea behind random forest is similar to the concept of wisdom of crowds. If we ask one person for an opinion, the answer may be biased or incorrect. However, if we ask many knowledgeable individuals the same question and combine their opinions, the final decision is often more reliable and more accurate. Random forest applies the same principle by combining predictions from many trees. Random forest follows four main steps. First, multiple random samples are created from the original dataset. Second, a decision tree is built from each sample. Third, each tree generates its own prediction. Finally, the predictions are combined to averaging or majority voting. This ensemble approach improves accuracy and reliability and reduces overfitting. Bootstrapping is one of the key techniques that makes random forest effective. Instead of training every decision tree on the exact same dataset, the algorithm creates multiple random samples from the original data. These samples are generated with replacement, meaning that some observations may appear multiple times in a sample while others may not be selected at all. Each bootstrap sample is then used to train a different decision tree. Because every tree sees a slightly different version of the data, the trees learn different patterns and make different predictions. When these predictions are combined, the overall model becomes more robust and less sensitive to noise. This diversity among trees is one of the main reasons random forest reduces overfitting and achieves strong predictive performance. In addition to using different observations, random forest also introduces randomness by selecting only a subset of features at each split. For example, if a dataset contains 10 predictor variables, the algorithm may randomly evaluate only 3 or 4 variables when determining the best split. This prevents the model from relying too heavily on a few dominant variables and encourages diversity among the trees. As a result, the forest becomes more robust and better able to generalize to new data. This slide illustrates how predictions are generated in a random forest model. Consider an asphalt mixture with known values of air voids, binder content, wrap content, VMA, and VFA. Each decision tree processes these inputs independently and produces its own prediction. One tree may predict a value of 85%. Another tree predicts a TSR value of 87%. Another one 84, 86, and so on and so forth. So the random forest combines these predictions by averaging them, producing a final prediction that is generally more reliable than any individual tree. This averaging process reduces the influence of noisy predictions and improves model reliability. Random forests can also be used for classification problems. Instead of predicting a continuous value, the model predicts a category or class. For example, an asphalt mixture may be classified as either pass or fail based on a tensile strength ratio threshold. Each tree independently votes for one of the classes, again, either pass or fail. The final prediction is determined by majority voting, meaning the class receiving the most votes becomes the final output. The voting process makes random forest highly effective for classification tasks because individual tree errors are often corrected by the collective decision of the forest. The middle box in this slide compares one single decision tree with random forest. So basically, the main difference is that in a single decision tree, there is only one tree, only one model. But in a random forest model, there are many models. And basically, when you have many models, it goes with lower variance and reduced overfitting, which makes it more stable and more reliable, more accurate, and it is also robust to small changes. Basically, this model is more accurate than a single decision tree. One unique advantage of random forest is out-of-bag error estimate. During bootstrapping, not all observations are selected for a given tree. The observations left out are called out-of-bag samples. These samples can be used as an independent validation set to evaluate model performance without requiring a separate test dataset. The out-of-bag error provides a reliable estimate of how well the model is expected to perform on unseen data. Feature importance is one of the most valuable outputs of a random forest model. In addition to making predictions, the model can identify which input variables have the greatest influence on the target variables. For example, in an asphalt mixture study, the model may indicate that air voids and binder content are the most important factors affecting tensile strength ratio, while other variables contribute less. These importance scores help engineers better understand the system being modeled and can guide future data collection, mixture design, and decision making. Once a model is trained, its performance must be evaluated. For regression problems, common metrics include R-squared, mean absolute error, and root mean squared error. R-squared measures how much variability in the data is explained by the model, while mean absolute error and RMSE quantify prediction errors. A good model typically achieves a high R-squared value and low error metrics. Evaluating multiple metrics provides a more complete picture of model performance. Random forest performance is influenced by several hyperparameters. Important examples include the number of trees in the forest, the maximum depth of each tree, the minimum number of samples required to split a node, and the number of features considered at each split. Increasing the number of trees generally improves stability but also increases computational cost. Selecting appropriate hyperparameter values is important for balancing accuracy and efficiency. Random forest offers several important advantages. It can model nonlinear relationships, handle large and complex datasets, and is generally less prone to overfitting than a decision tree or single decision tree. The algorithm also works well with both categorical and numerical variables and can provide feature importance rankings. In many practical applications, random forest delivers a strong predictive performance with relatively little parameter tuning. Random forest comes with its own limitations. Because it consists of many trees, the model can become computationally intensive for large datasets. Additionally, although random forest is more interpretable than some advanced machine learning models, it is still less transparent than a single decision tree. The ensemble nature of the model can make it difficult to fully explain individual predictions. This slide illustrates how random forest can be implemented using Python and scikit-learn. The typical workflow includes loading the dataset, splitting it into two groups of training and testing datasets, creating the random forest model, training the model using the training data, and evaluating its performance on unseen data. Python libraries make this process straightforward and allow researchers to quickly develop predictive models for engineering applications. Here is a summary of the main concepts covered in this presentation. Random forest combines multiple decision trees through bootstrapping and random feature selection to produce accurate and robust predictions. The model reduces overfitting, handles nonlinear relationships, provides feature importance ranking, and performs well for both regression and classification problems.